Okay guys, next we have common collector configuration of transistor. First I will plot a transistor. Here we have, this is the base, this is the emitter, and this is collector. So this is base, here this is emitter, and this is collector. Now in common collector configuration, the collector is common between base and emitter. So here this is the collector which is common between base and emitter. So this is called common collector configuration of transistor. So in common collector configuration, the input signals the input signals are applied to this terminals, like to the terminal base and collector terminal, while the amplified output signal can be obtained can appear at this terminal, like between here emitter and collector. So signals are applied at the input terminal like collector and base, and amplified signal appear at the output terminal like the emitter and collector. This is the output terminal. So this is called common collector configuration of transistor. Now this is one notation for the common collector configurations. Now if I use the Npn transistor, okay, this is my Npn transistor. So this is N, this is P, and this is N. Npn transistor. Now this is emitter because this is collector because its width is bigger than this P and this N. So this is collector, this will be emitter, and this will be the base. So here we have this collector, emitter, and base and emitter. Now the collector is common between base and emitter. Okay, so here this is the collector which is common between base and emitter. The collector is common to both input and output. Now in order to, when a transistor is working in active region, like in active region, we have two junctions here. The junction between emitter and base is J1, and the junction between base and collector is J2. So in active region, when a transistor working in active region, then junction J1 will be forward bias and junction J2 will be reverse bias. So in order to make this junction J2 reverse biased, we will connect it with the battery. So here this is the battery. So this will be the negative terminal of the battery, and this will be the positive terminal. So the negative terminal of the battery is connected to the P region, and positive terminal is connected to the N region of this junction J2. So this makes this junction J2 forward bias. Now in order to make this junction J1 reverse bias, so we will use another battery here such that N is connected to the positive terminal and P is connected to the negative terminal. Now this junction is forward bias, J1, which is forward bias now. Yes, this is forward bias. So we can say that if I call this battery as VBB, because it is connected to the base terminal, so this VBB, this battery VBB makes junction J2 reverse bias, sorry. And similarly, if I call this battery as VEE because it is connected to the emitter terminal, then we can say that the battery VEE makes the junction J1 forward bias. Now there is a voltage appear between these two terminals, so we represent that voltage by VCB here, because the voltage appear between this base and collector is represented by this VCB. C, here we keep C first because collector is connected to the positive terminal and base is connected to the negative terminal. So the positive terminal indices is come first and the negative terminal is come second. And similarly here, the voltage between this emitter and collector, which I represented by V, and we have EC. Now if you look at here, the emitter current is always inward. This is the emitter current, and we know that we have a relation that emitter current IE is equal to IC plus IB. So if emitter current is inward, okay, if emitter current is outward, yes. This is the emitter current which is outward. So the collector current and base current will be inward. So the IC direction will be this one and IB direction will be this one according to this relation. Now in case of common base configuration, okay, I call it equation number 1. In case of common base configuration, okay, we have a relation which is IC is equal to alpha IE plus ICBO. This is equation number 2. Now this equation number 2 shows a relation between output current. This is the output current and this is the input current. So this equation shows a relation between output current and input current. Now in common collector configuration, here we have the input current is, if you look at here, the input current is IB and the input voltage is VCB. Similarly, the output current is, here the emitter current is output current and the output voltage is VEC. Now if we look at here, we have the output current IC, which is a function of input current IE. This is the case for common base configuration. So it means that for common collector configuration, we will also I will CC, common collector configuration. We will also derive a relation which will represent the input current, the output current which is IE, which will be a function of the input current which is IB. We will derive a relation like this, like what we did in common base configuration. So here this is the output current and IB is the input current. Similarly here IC is the output current and emitter current is the input current. So here I will derive a relation like this for this common collector configuration, like what we did in the common emitter configuration. So for that I will use equation number 2 and equation 1. Before going further into detail, I will define another terms here, which is current gain in common collector configuration. So the current gain in common collector configuration is represented by this gamma. Okay, this is the current gain in common collector configuration, and this current gain is always defined to be like this. Like we have the output current or input current. So in common collector configuration, the output current is IE and the input current is IB. So this is gain. Now I call it equation number 3. Yes. Now using equation number 2 and equation 1. So we have equation 1 and equation 2 here. So using equation 2 and 1, we have, so equation 1 is IE is equal to IC. Instead of IC, I will put equation number 2, so which is alpha IE plus ICBO, and then we have plus IB. So if I put equation 2 in 1, I have this relation. So here we have IE and here we have IB. So I will bring this term to this side. So I have IE is common. So here I have 1 minus alpha, which is equal to IB, this term, plus ICB. I can write IE is equal to, if I bring this term to this side, then I have 1 over 1 minus alpha IB plus 1 over 1 minus alpha ICB. Now in case of we know that we already derived this relation in the common emitter configuration, that beta plus 1 is equal to 1 over 1 minus alpha. We already derived this relation in case of common emitter configuration. So using these values in above equation, so we have the emitter current, the output current, which is equal to beta plus 1. Instead of 1 over 1 minus alpha, I will put beta plus 1 into IB plus, and then we have again beta plus 1 into ICBO. Now where beta is the current gain and common collector configuration, and it is defined to be like this. Beta is equal to the output current in common collector configuration is IC, common emitter configuration, sorry, this is common emitter, like the topic we discussed before, where beta is the current gain in common emitter configuration. In common emitter configuration, the output current is IC and the input current is IB, the base current. So this is the current gain in common emitter configuration. Now we have equation number 1. I can write equation number 1 is like this. Equation 1 is IE is equal to IC plus IB. Now dividing throughout by IB, dividing this equation throughout by IB, we have IE over IB is equal to IC over IB plus 1. Now IE over IB is the current gain in common collector configuration, which is gamma, because we already defined gamma here, equation number 3. So this is gamma, which is equal to IC over IB, which is basically the current gain in common emitter configuration, which is represented by beta plus 1. So it means that gamma is equal to beta plus 1. So if I replace this beta plus 1 here, this beta plus 1 by gamma, then this equation will become like this. IE is equal to gamma into IB plus gamma into ICB. Gamma into ICB. So this is the equation like what we did in the common base configuration. IC is equal to alpha IE plus ICB. They have the same form, because here the output current is IC, here the output current is IE, here the input current is IE, here the input current is IB, plus we have this leakage current. We are here ICBO is the leakage current, or we can also call it the reverse saturation current. The reverse saturation current between collector and base. Collector and base, and when the third terminal is basically emitter is open. This is the reverse saturation current between collector and base terminal, when the third terminal, which is emitter, which is open. So this it means that emitter is open, and this is the reverse saturation current between collector and base. Now here we will replace gamma into ICBO by IECO. So if I replace it by this one, then my emitter current, the output current, is equal to gamma times the input current, which is IB, plus gamma into ICBO is replaced by IEC. This is the final expression for the common collector configuration. Now in the next video, I will discuss the common collector configuration, input configuration, or the common collector input characteristic and output characteristics, and then we will move to another topic. Thank you.